Hello and welcome. Today, we're going to peek behind the curtain of the world around us. We're going to explore all these invisible forces, these hidden rules that decide how a ball flies through the air, how a car makes a turn, and even how you walk across the room. It all starts with a question that, you've probably never really stopped to think about.
It seems like such a simple question, doesn't it? I mean, why does a shopping cart need a push to get going? And hey, once it gets rolling, what's stopping it from just rolling on forever? Well, the answer gets right to the very heart of physics, and it all comes down to this constant battle of pushes and pulls.
All right, so here's our game plan for this explainer. We'll kick things off with the basic reason things move at all. Then, we'll dive into the fundamental laws that run the whole show. We're going to tackle that tricky but super useful force, friction, see how we manage it. And finally, we'll take a little spin with the physics of circles.
So let's jump right into that first question. Why do things move? And the answer isn't just, well, because I pushed it. It's actually a little more specific than that. It's all about an imbalance, a hidden tug of war that's happening everywhere all the time. And this right here, this is the big one, the most important rule of them all. An object is going to keep doing whatever it's doing, whether that's just sitting still or moving along, unless an unbalanced force steps in. Think of it like this. If all the pushes and pulls cancel each other out perfectly, nothing changes. But the moment one force overpowers the others, that's when things get interesting. That's when you get acceleration. Let's bring this down to Earth. Just picture a regular old office chair on wheels. When you give it a shove, your pushing force is stronger than the friction from the floor, right? That's your unbalanced force, and boom, the chair accelerates. But what happens the second you let go? Well, your push is gone. Now friction is the main force in town, and it slows the chair right back down to a stop. So simple, but it really does govern everything.
Now, knowing that an unbalanced force makes things move is one thing. But, how do we actually describe that relationship? Like, how much go do we get for a certain amount of push? Well, lucky for us, some guy named Sir Isaac Newton basically wrote the rule book on all this. And here it is, the famous one, F equals ma. I mean, this little equation, it might just be the most powerful one in all of classical physics. It's Newton's second law, and it just perfectly connects force, mass, and acceleration. It's the recipe that tells you exactly how an object is going to react to a push. Let's see what that really looks like.
So let's break that down into 3 really simple ideas. First up, if you double the force on something, you're going to double its acceleration. Push twice as hard, it speeds up twice as fast. Totally makes sense. Okay, what about the second one? What if you use that same force but on something with twice the mass? Well, just like you'd expect, the acceleration gets chopped in half. And finally, an object is always going to accelerate in the exact same direction you're pushing it. These might feel obvious, but that little formula is what proves they're always true.
Now, this next one. This is probably the most famous law in all of physics, and for a really good reason. It's Newton's third law, and it points to this beautiful fundamental symmetry in our universe. Forces never, ever show up alone. They always come in pairs.
So here's a perfect example of how these pairs work. Just think about a book sitting on a table. The book's weight is a force pulling down on the table. That's the action. At the exact same instant, the table pushes back up on the book with an identical but opposite force. That's the reaction. And because these forces are equal and opposite, and they're acting on 2 different things, the book and the table, everything stays perfectly balanced. The book doesn't move. This, by the way, is also how rockets work. They push hot gas down and out, and that gas pushes the rocket up, equal and opposite.
All right, we've kind of danced around this one a few times, but let's put it right under the microscope. Friction. It's the force that always tries to stop motion. It's this unseen grip that's both a hero and a villain in our daily lives.
I mean, on one hand, friction is just absolutely essential, right? It's the only reason you can walk without your feet just slipping out from under you. It's how a car's brakes can actually bring thousands of pounds to a stop. But on the other side of the coin, it's a total pain. It's what causes parts in an engine to wear down, and it robs our machines of energy, making them less efficient. It really is a constant battle.
So because of this, this love-hate relationship, a huge part of engineering is really just about mastering friction. We've spent centuries figuring out how to get rid of it when it's in our way and how to ramp it up when we really need it. So, when friction is the bad guy, how do we fight back? Well, we get smart. Instead of dragging things, we put them on wheels, which swaps out tough sliding friction for much weaker rolling friction. For things that spin, we use these amazing little things called ball bearings. We add slippery stuff like oil and grease so surfaces just glide past each other.
And in really cool cases, like a hovercraft, we just lift the whole thing up on a cushion of air and get rid of almost all the contact.
But then there are times when we want more grip, not less. And this is where we get creative to increase friction on purpose. Those deep grooves on your car's tires, they're designed specifically to channel water away and maximize the tire's grip on a wet road. A parachute, it's all about having a massive surface area to create as much air resistance, which is just a type of friction, as possible. Even a rock climber puts chalk on their hands just to increase the friction between their skin and the rock.
Okay, so everything we've talked about so far has been about motion in a straight line. But what happens when things start going in circles? Whether it's a planet orbiting the sun or you taking a sharp turn in your car, a whole different set of rules kicks in, and it's all run by one very special kind of force.
Yeah, let's think really big for a second. The moon. It is moving so fast. Now, everything we've learned says it should want to just fly off in a straight line forever, right? So, what's constantly pulling it back, forcing it to curve its path around the Earth? Well, the answer is something called centripetal force, and the name literally means center-seeking. Now, this isn't some new, mysterious force on its own, it's more like a job description that other forces can have. For the moon, that job is done by gravity. For a car turning a corner, it's the friction between the tires and the road. It's any force that is constantly pulling an object toward the center of its circular path.
And you knew this was coming. Of course, there's an equation for it. This formula tells us exactly how much of that center-seeking force you're going to need. And look what's in there: mass, velocity, and the radius of the circle. This tells us that a heavier car needs more force to make a turn. A faster car? Oh, it needs way more force. See how that velocity is squared? And a really tight turn, that's a small radius, that also needs more force. And that is why you instinctively slow down for sharp corners.
Okay, now this brings us to something that trips a lot of people up. You know that feeling when you're in a car, making a sharp turn, and you feel like you're being thrown outward? People often call this centrifugal force. But here's the big secret. It's not actually a real force. What you're feeling is simply your own inertia. Your body wants to keep going in a straight line, but the car door is pushing in on you, forcing you to turn with the car. That inward push is the real force. That outward sensation is just your body resisting the change.
So there you have it. From the simple act of pushing a chair across the floor to the grand sweeping orbit of the moon, the same fundamental rules are always at play. Unbalanced forces make things change, every single action has a reaction, and going in a circle always needs a constant pull toward the center. So the next time you walk, drive, or just watch the world go by, I have a challenge for you. Now that you can see these hidden rules of motion all around you, what force are you going to notice first?